Hi, I'm going to report on ongoing research on relational reasoning in object-based programs. This is joint work with Dave Norman, Ramana Nagasamudram, and Mohammed Dekoe from Stevens Institute of Technology. There are a variety of contexts in which one may be interested in relational reasoning. For example, one may be interested in equivalences between two programs, or program transformations, or compiler optimizations. Here's a simple example where we want to show that the two assignments in C0 can be commuted to obtain the program in C0 dash. Here f and g are pure, that is side effect free functions, and we want to show that C0 and C0 dash are equivalent. Now one can construct a Unary specification for C0, and that is given in this format here with the squiggly arrow. So to the left of the squiggly arrow is the precondition that says z equals n. And the postcondition says x equals f of n and y equals g of n. And then there's a frame condition that says that x and y may be written and z may be read. Okay, and both C0 and C0 dash have the same specification, and so they can be considered to be equivalent. But in general, although this is a simple example, in general, the full specs needn't be available, and yet one can show equivalence of C0 and C0 dash by reasoning in a relational manner. So we can say that if the pair of pre-states agree on Z, any terminated pair of post-states of C0, C0 dash, of the pair C0, C0 dash agree on X and Y. And this is how we write it. For the pair C0, C0 dash, agreement on Z in the pre-state gives agreement of X and agreement of Y in the post state, together with the frame condition that X and Y may be written and Z may be read. This is our first example of a relational spec, and it's relational because we are considering two states corresponding to the two runs of the program and relations between the states. And this A, which is pronounced as agree, so in two states, sigma and sigma dash, agree of Z holds if and only if sigma of Z equals sigma dash of Z. That's one example of relational reasoning. Sometimes the property that you may be interested in is relational by itself, like noninterference. And here is an example of that. So suppose we want to sum the elements of a singly linked null terminated list pointed by P, ignoring all high security nodes for which the flag pub is false. So for the high security nodes, the flag pub is false. And for low security nodes or public nodes, the flag pub is true. So noninterference says that the sum is independent of values of the high security nodes and only depends on initial values of public nodes for which pub is true. So here is the program that represents this particular sum that we're interested in. So the program C1 initializes S to 0 and then loops on P not equal null, and it checks if P dot pub holds, in which case you do the sum, otherwise you skip and go on to P dot text, the next element in the list. And so noninterference basically says in two runs of C1, if initial values of the public nodes agree, then the sum agrees. That's what's represented by this relational formula, C1 paired with C1 itself, has the relational spec, where the precondition is agreement on list pub P, and the postcondition is agreement on S. And list pub P here just says that's a function that talks about the mathematical list of values in public nodes reached from P. Okay. The next example is data abstraction. And this is the main example that we will be looking at for the rest of the talk. And this says that here we are interested in change of data representation. So this is familiar to you from, say, ADTs. So suppose we have a stack ADT, and in one implementation of stack, we use the representation of a linked list, and in the other representation we use the implementation of an array. Okay. So what we have here is that we have the same interface, but different implementations with different data representations, and yet we want to show that the clients of stack behave the same despite different data representations. How can we prove that? Can we reason about that using a program logic? Okay, so let me just mention here that this annotation spec public basically says that these are variables that cannot be modified by a client, but they can appear in specs and can be used by the client for reasoning about the program. Okay. All right. So now what we want to show is that linked clients behave the same. And so if the client is of the form push 1 followed by an allocation p gets new node followed by the field update p.val gets 3 and then push 4, what we want to show is that the two linked programs C4 and C4 dash, which are represented as follows, which let push s equals b. This is the body. This is the implementation of push s, which is an interface method in cli. Okay, so that program C4 is equivalent to let push s equals b dash in cli. So the cli's are the same, but the implementations of push are different. Why do we care about showing this equivalence? Well, it's because we want to free, this is from a software engineering point of view, we want to free the client programmer from dependence on internal representations. And we want to free the library programmer, that is the designer of the module of stack. We want to free the library programmer from needing to reason about specific clients. So here is where we have another example of a relational property, and that is simulation. And to show this kind of equivalence, what we typically do is define a coupling relation L to relate the two data representations and data invariants for each representation, and then show that B and B dash simulate to each other via L. Remember that B and B dash are the implementations of push, the two different implementations of push. So semantically, since Hoare 1972 and Reynolds 1984, we can represent the situation by this diagram. So suppose we have the initial state sigma for the implementation B, and B transforms sigma into the state tau, and likewise we have sigma dash and tau dash for B dash. And suppose sigma and sigma dash are related by this relation L, this coupling relation L, then that implies that tau and tau dash must also be related by L. Okay, this is a very semantic way of talking about simulation. Right? And we want to capture this kind of reasoning in a program logic. Okay, so here we have something that will appear very shortly, namely the Unary spec of push. Right? And this is a very simple spec of push that just says if the size, in the precondition it says if the size is less than 100, then the postcondition says the size is augmented by 1. Size is equal to old size plus 1, where old size refers to the value of size before, in the pre-state of push, right? And then these are the this is the frame condition here that says that the readable and writable locations, this RW, these include rep, size, rep image any. We pronounce this as rep image any, and read s. And rep image any says all fields of all objects in rep may be read or written. Okay, I'll come back to that in a bit, but that's basically the frame condition of push. And we can write this thing as R arrows S eta, where R is the precondition, S is the postcondition, and eta is the frame condition. So that we did that just because we want to express simulation and equivalence as relational formulae that can then form that can be verified using a program logic or a prover. Okay, so we have seen what C4 and C-4 are. These are the linked programs, comprising of the linked client with the two different implementations B and B dash. Here is the client that we have seen before, push 1 followed by an allocation, followed by p dot val gets 3, followed by another push. And sorry, the simulation basically says that for the bodies, the two bodies B and B dash, remember that diagram. What we said there was that there was the initial states were related by L, and the final states were going to be related by L. So in this formula, that is depicted by the preservation of L. So the L is the same in the precondition and the postcondition, and L is relational. Okay, we will see the exact shape of L later on, but this is, if you don't worry about these other things, but except that R and S are the pre and post conditions of the unary push that we have seen earlier, and B of R and B of S are pronounced as both of R and both of S, and that basically says that R holds both in both states. So sigma dash satisfies both of P if and only if sigma satisfies P and sigma dash satisfies P. But the point I want to make about simulation is that this relation L is preserved in this relational formula. And then equivalence says that for the linked programs, we have the following situation. If I knew that both initial states satisfy the precondition size equals 0, then the postcondition says that there is agreement on all client visible locations, and thus the two linked programs are equivalent. So there is agreement on P, agreement on size, and agreement on P image any, that is agreement on all fields of all objects represented by P. Okay. All right. So this is so that's the notion of equivalence. Okay, and these are given as relational formulas, and we can prove these using a program logic. Okay. So then the main question then is, can we obtain a general program logic with which we can perform the varieties of relational reasoning? Okay, not just the relational reasoning pertaining to data abstraction, although that would be the main focus in this talk, but also noninterference, program equivalence, and so on. What are the ingredients of this reasoning? Well, there is going to be a unary logic, which we dub region logic, and on which we have been working since 2007. So this unary logic for functional correctness under hypotheses. Why under hypotheses? Well, because we have procedures, methods, right? And these, and you want to reason about the bodies of the methods and the clients which use these methods, and so there have to be hypotheses. You need to know what is the spec of the particular method that you are utilizing. So then we also need procedure modularity. The logic should have support for procedure modularity. That is, we must reason only with the spec of push in a stack client and not again go and reason with the implementation of push, right? Just the spec of push in stack client. The Unary logic should support encapsulation for hiding. You don't want the internal invariants to be exposed at the interface, right, and in the specifications of the interface, because you don't want the clients to have anything to do with establishing any internal invariants. So that is why we need to designate internal or owned heap locations of a module. This owned is from ownership terminology, ownership types, and so on. But basically what that says is that there are some internal heap locations which are designated, which have been designated, and these we must make sure that clients respect encapsulation. That is, they don't read or write these owned locations. Okay, and so the Unary logic has this kind of judgment, which says that the phi is the hypothesis context, which means that it maps method names to their specs. C is the command that doesn't call methods outside their preconditions and doesn't interfere with the encapsulated state of any module in phi other than its own. All right, because you don't want. So why is it the case it doesn't interfere with the encapsulated state? Because then it'll break invariants of other modules. Okay, but for its own module, it's completely okay, right? Because you expect that when it calls a particular method, a module method, that method is going to write or read internal state of its own, of that module itself. By that I mean the module in which that method is declared. Okay, that's Unary logic, and then we want a relational logic with framing and encapsulation, and we want to use relation formulas, as we have seen before, to define couplings and specs, and we want to make sure that we can reason about simulation, that is, prove preservation of these couplings, and we must designate alignment of intermediate steps, exploit similarities, and handle differences. And we are going to see alignment in the very next slide, but basically alignment is saying when is it that we can assert relational formulas. Okay, so to understand alignment, it helps to go back to Floyd's inductive assertions methods for partial correctness. What does it say? It says you establish conditions, establish that certain conditions in which you're interested hold at intermediate computation steps, associate formulas at control flow points in flowcharts. So Floyd's method deals with flowcharts, but basically the idea is that you associate formulas at control flow points in the flowcharts. And the advance of Hoare's logic from 1969 was to designate the control flow points in structured syntax, right? And then use a program logic to reason about these properties, and that's Hoare logic. Now, we want to lift Floyd's inductive assertions methods to pairs of programs, right? Because we are dealing with the relational case, so we have pairs of programs, and we want to lift Floyd's inductive assertions methods to that. What that means is that we have to establish relational conditions at pairs of intermediate computation steps. And we have to associate relational formulas at aligned pairs of control flow points in off-to-cut loops. Okay, so the whole thing boils down to what are the aligned pairs? How can you talk about the aligned pairs? So we do that by designating alignment in program syntax, and we call these biprograms. So we've already seen one kind of biprogram, and this pair CC dash we call a split biprogram that represents executions of C dash which are aligned on their initial states, and if they terminate on their final states. Okay. And on the other hand, we can have what is called a sync biprogram that says, well, consider left and right transitions in lockstep. Okay. And the point is that when we have pairs of programs, then we can try to weave them into a single aligned biprogram so that we can assert relational formulas. So if the two sides are the same, so L gets n plus 1, L gets n plus 1, then we can weave that to a synced biprogram L gets n plus 1. And what we expect is that a relational formula will hold before and a relational formula can be established afterwards. On the other hand, if we have a split biprogram of this form, C semicolon D split C dash semicolon D dash, then that will weave to C split C dash semicolon D split D dash. Okay, and we'll see an example of this very shortly. All right, so a change of data representation. This is a slide that we have seen before, but this is just as a reminder. So we have the module stack with two different implementations, one with a linked list and the other one as an array. This is the client. This is the linked client with the two implementations, and finally this is the relational formula that we want to prove of the split biprogram C4 C-4. Okay. Now we can weave the C4 C-4 because each one is of the form let push s equals b incly, and the other one is let push s equals b dash incly. Notice that cly is the same, right? So we can sync them, and then we can split the implementation so that we get a synced we get this kind of a biprogram let push s a let we call it let push s equals b split b dash in sync of cly. And the whole point is that although you expect that b and b dash are two completely different implementations of push, one as a linked list, one as an array, but nevertheless the client is the same, and the client's execution steps must be synchronized. Okay, so that we can establish relational formulas at every step of the implementation of the execution of the in every step of reasoning about the client. So here is what I mean by a synced client. So sync cly would basically mean that every every component of cly is synchronized, right? And so it suffices to prove this ultimate result that we want, that right, for the woven program, which is let push s equals b split b dash and cly. It's enough to do that by soundness of weaving. Okay, we have a weaving rule. I don't want to get into that here, but that's how that's all that we need to prove. So weaving for b split b dash, these are the two implementations, and this shows you something interesting because there are pieces of b and b dash that are completely different, right? So the first two commands are here, and the if then else, these are completely different. Okay, so these can be split, right, because they're completely different, and what we expect for that split is that if in the beginning, right, some relational formula holds, then at the end of the split some other relational formula will hold. Okay, but the intermediate steps the relational form, there need not be any kind of relational formula holding between the two sides. Okay, so these are, so you would do unary reasoning for each component of the split. Okay, but then at the end, both of the bodies have size, increment of size that can be synced. Okay. So what we want to do is to expose the aligned pairs in the clients and in the implementation bodies B dash. So we have already seen how we have exposed the aligned pairs in the client, but this is how we expose the aligned pairs in the implementation body. Here there's only one aligned pair, size plus plus. This is synced pair. And then for the other one, it's split, right? For the rest, it's split. And we can then apply syntax-directed relational reasoning. Okay, so I have been talking. Let me just repeat one little thing, which is that for the split, to reason about the split, you need unary reasoning. That is why we needed the unary logic, and we can then combine the individual specs, arising out of the unary reasoning on both sides by embedding into relational spec, which we then use for reasoning about the synced program size plus plus. Okay, I've been talking a lot about the coupling between these internal data representation. So this coupling L relates the stack and array data representations and the hidden data invariants I and I dash for each representation. Right, so remember that for every representation, if you want to reason about correctness of each representation by itself, right, you will have to have some internal data invariants. So those are I and I dash, and I will come to that very shortly. But what L is saying is instructive. So L is a relational formula. It says left of I and right of I dash and something which is equal. So let me say what left of I means. Left of I basically is a relational formula, but basically it's the relational lift of the unary formula I. So in two states, sigma and sigma dash, left of I holds, provided in the left state sigma I holds. And likewise for right of I dash. Okay. So L is the conjunction of left of I and right of I dash. And then this thing is written as list of top by equals reverse of slots of 0, free, minus 1. And that basically says that in both states, that is a relational formula that by equals. And so in sigma, sigma dash, list of top by equals reverse of whatever, if and only if sigma of list of top equals sigma dash of reverse. Okay, well, what this is saying is that the mathematical list that you obtain by traversing from top is the same as, is equal to the mathematical list that you obtain by considering the values in the array slots 0 to free minus 1 and reversing that. Okay, so let us see what I and I dash are. Let me just talk about I, because I dash is similar. I is an internal data invariant in the case of the implementation as a linked list that just says either it's the case that top is null and size is 0. So the size of the stack is 0. Top equals null and the size of the stack is 0. Or top and rep. Remember that rep is holding encapsulated locations, okay, and rep image next is in rep. So the list is basically is closed under next, and all the nodes are in rep, and the size of the list is equal to length of list top. Right, so if you traverse from top, whatever mathematical list you get, that length of that list is equal to size. Okay, so that is the coupling L. And how do we do the verification? So this is interesting because what we want again is that this linked client satisfies this relational formula. So the way we do the verification is to say that, well, show that B split B dash satisfies its spec. But what is that spec? Well, it seems like it's going to be the relational spec of push. But it's not just that. That relational spec has to be conjoined with the coupling L in its pre and post conditions. Okay. And then we have to show that the synced cli satisfies the overall spec, namely this both size equals 0, etc., under the hypothesis that push satisfies its relational spec. Okay. So again, recall this unary spec of push, which is of the form R arrows S eta, where R is size less than 100, S is size equals old of size plus 1, and eta is the frame condition, which says rep size, rep image any can be read or written, and S may be read. So this is the unary spec. Well, what is the relational spec? The relational spec is interesting. So remember that R and S were the unary pre and post conditions. So for the relational case, we would have to have both of R and both of S, right? Because they're talking about in two states. So in two states, R and S must hold. In both states, R and S must hold. But there is something more, namely that L must be preserved, right? And not only that, there has to be, so L talks about the encapsulated locations, but it's not only that, there has to be agreement outside the encapsulated locations. And outside the encapsulated locations are these size and S. And so there have to be agreement on size and agreement on S, and then in the post, you will have to have agreement on size and agreement on S, but we don't care about agreement on S. The point to note here is that this relational spec of push is not just a relational lift of push's unary spec. Were it that, this would have just been both R to both S eta. But it's not that. There is something more, right? And we can show that the woven B split B dash satisfies this relational spec phi by reasoning in the logic. I'm not giving you the rules of the logic, but we can show this. And then we can show that under phi, this synced cli satisfies this overall spec that we want. Okay. I haven't talked at all about the relational logic or give, in any detail, but let me at least tell you what the specs look like. You've seen how the specs look like, but let me tell you the meaning of the spec. So if we have this kind of spec, P arrows Q, epsilon, epsilon dash, P and Q are binary relations on states, and epsilon, epsilon dash are frame conditions, and this means that for all pairs sigma, sigma dash of P related states, meaning that sigma and sigma dash are in the relation P, a pair of terminating runs of the corresponding biprogram yield final pair of states tau and tau prime that are Q related. That is, tau and tau prime are in the relation Q. The two runs conform to the frame conditions. That means whatever these runs do, the reads and writes are given by the frame conditions epsilon and epsilon dash. And moreover, the relations must account for different allocation behavior. So if you have x gets new in one run and x gets new in another run, these two programs will not necessarily yield the same location for x, right? Because the two runs can have different allocation behavior. So there's a way to incorporate that in the semantics, and then we can reason in the logic. Okay, so the current work that I've reported has a proof rule for linking that incorporates hiding. And what hiding means is that hiding that L in this context, L doesn't appear in the public relational spec of push, though it is used to verify the implementation B dash B split B dash of push. That is exactly what we saw on this slide, right? So to verify the implementation B dash, you need that push has the L conjoined to both pre and post. And then we can lift this local coupling L, because this L is on encapsulated state, and we can lift this to L hat on global state. The implementations B and B dash simulate each other via L, and L hat is the identity on observable state. And that is what we observed in this example by this agreement P, agreement size, agreement P image any. That is the observable state to the client, and there is agreement on that state. And that's why I say here L hat is identity on the observable state. And by the way, Reynolds would call this kind of thing here, this local that the implementation simulate each other via L is as the abstraction theorem, and this L hat is identity on observable state as identity extension. What we are doing now is a prototype implementation for the unary and relational reasoning with heaps. That's going on, and in fact we are also using this implementation to see whether or not we have, our rules can handle the examples, and we are testing our logic on a variety of examples like Dijkstra's shortest path example, shortest path algorithm, Kruskal's minimum spanning tree algorithm, and others. Okay, so some closely related work. Nick Benton and Hongsuk Yang are the precursors to all of this work that I've mentioned here. Benton started with this idea of relational horror logic applied to program transformations and non-interference in the context of simple imperative programs. Both he and Yang consider programs with similar control structure. Okay. But that need not always be the case, and we in fact consider both similar and dissimilar control structure. Yang considers relational separation logic that incorporates the heap. This is a series of papers by Gilles Barthes and his students on construction of product programs from program pairs with similar and dissimilar structures, and they handle for all their exist properties for simple imperative programs. Then there is the work by Godlin and Strickman, who provide sound rules for proving equivalence of programs with similar control structure. They are implemented in equivalence checking tools. They handle pointer structures with no sharing, which of course we allow. And then finally, there's the work by Hobletzel et al. And Lahiri et al. On intra and interprocedural reasoning about transformations. They have relational procedure summaries, and they have heaps, which are modeled by maps. So the main takeaways are threefold. Through the stack example, we have seen examples of state-based encapsulation, hiding of invariance, and we have alluded to a proof rule for equivalence of linked programs. And we have, in this manner, talked about modular reasoning about unary and relational properties of object-based programs. What I haven't spoken about is that this formulation that I described today leads to semi-automated reasoning, because all formulas and specs in our logic are first order. So we can use automated provers to reason about correctness. And we have a foundational justification. That is, we have proven soundness of our proof system based on accurate program semantics together with a modeling of dynamic allocation. So that's all I have. Thank you very much. Bye.